Hello. I am speaking to you from Hawaii today. I'm going to just pause for a second here. And it's just about 10 a.m. in Hawaii. So you can see what I have in my laboratory here. And I'm going to move the camera around a bit so you can see what's going on here. There's the periodic table of units of measure we'll be going into in a minute. And now I'm going to give you a little speech about this mass equals area theory. And then I'll be going into units of measure that are all changed when we consider this abstract concept here. Hello, it's Alan Folmsby here. Thank you for stopping in again on this live broadcast on YouTube streaming. And today I'm going to be talking about some mathematics, and supporting this mass equals area theory is some authority figures who have published papers before, and I'll be telling you about the geometry and the concepts of the liquid space and how mass is an area of liquid. And then I'll go into some algebra where I can show a new type of tool for physics. It's called the Composit Formula. So I'm going to bring up these PowerPoint slides for you now and show you some of the details. So on the authority side of things, I'm not the first one to say that space should be treated like a liquid. There were other people here in 2008. Mr. Hamilton and Lyle had this paper, A River Model of Black Holes. So what they're saying is they're treating space like a liquid, a river. Now there's another paper that was inspired by that one, and it's called A River Model of Space by Brake and Grahn in 2013. So they have then picked up on the liquid theme, like I am also today in 2019, carrying on. And if you read these papers on the internet, they're freely available. You can see that all kinds of relativistic things are accurate when you treat it this way. Now, as far as the geometry, and the mass equals area of a liquid is the geometry. In other words, gravity's created by a volume consuming a liquid, and then mass is pulled in with the gravity as if each particle had a little parachute or a sea anchor. It's an area in a liquid that will then pull the mass along and accelerate it. And this talk today is using abstract possibilities for consideration. That it's not just mathematics that has abstract math. Also physics can use geometry with abstract considerations of mass equals an area. Or you could make up your own thing saying a kilogram is never factorable, that it is a prime number, that it's not a composite like I claim. Now I'm going to do three things for you immediately. I'm going to show you the algebra using the composite formula, something new for you. And then from this mass equals area theory, I can show you that the atomic scale formula, why are atoms a certain size and really no bigger? And then finally I'll show you the replenishment power formula taken from all of this unification here. So here are those three ideas. The composite formula says that a kilogram times a farad of capacitance is equal to a square meter times a square second. I'll be going into that in great detail soon. Now, the second new idea I'm telling you about is the atomic scale formula. Here it is. 2.41 angstroms is equal to Q, the electron charge, over 4 pi a. The Bohr radius is a. It's about an angstrom, half an angstrom. And then that is also equal to m, the proton mass, divided by r, the proton radius, and alpha, which is the fine structure constant, 1 divided by 137. Now, this 2.41 angstroms happens to be about the size of the largest atom, potassium. There's only, I think, one other element that's a little bit larger than this, but potassium is 2.43 angstroms, and every other element's a little smaller than this, but larger than a Bohr radius, A, which is about 0.53 angstroms. So I'm unifying gravity, inertia, and electromagnetism along with atomic electromagnetism and Planck's constant. And that occurs in this third formula, the replenishment formula here. You see that gravity is replenishing Planck's constant using that 5 nanosecond time constant tau. And here's the formula. The replenishment power for each proton-electron pair is 2.51 electron volts per second. And that's calculated from Planck's constant, h bar, divided by tau squared, 5 nanoseconds squared. So that's useful for laser beams. I already brought that up in an earlier lecture about the erbium fiber optic laser calculation, where this replenishment is what is feeding the states for population inversion. And so today, under the mass equals area theory, we're able to go from old units of measure to new units of measure. And these things are summarized as right here. So in electrical engineering, we commonly use Maxwell's equations, which has the H field and the E field in this slide here. Now H is the magnetic field intensity, and they used to say it was amperes per meter. And now under the new wisdom here of mass equals area, H, the magnetic field intensity, is a velocity. It's not, doesn't have to be called amps per meter. Equivalently, it is called velocity. You decide which one's more meaningful. Magnets moving with a velocity, or magnets moving with amps per meter. And they're both true, they're both wise, but the Weber, on the other hand, is said to be a volt second. That's a magnetic flux. Now, in the new way of thinking, the Weber is square meters per second. So that's a flux, much like the ampere is coulombs per second. And if coulombs were an area, then that would be square meters per second. All right, the third example here is ohm. Now, in the old units, ohm was just said to be a volt per amp. Now, in the new units, the ohm is 1/second per second. So what it's saying is the ohm is the number of events per second that's slowing down the current. And if there's a lot of events going on, then there's a lot of resistance. All right, and finally the E field, the electric field of Maxwell's equations. They were saying it's volts per meter. And under the new units, it is acceleration, meters per second squared. So I'm going to move the camera around a bit here, so you can just look at some dark matter while I'm moving the camera. All right, I'm almost ready to show you what I've got here. But give me a second. All right, here comes the new information here. The periodic table of units. I'm not going to derive mass equals area immediately. First, I want to show you the good news that comes on as a result. So here's in the gravity continuum, the periodic table of units of measure. You see across the top axis of the table is seconds, or different powers of seconds, per second, per second, per second, second to the minus third power. And on the left axis, you see the vertical of this array is meters to different powers. So the goal of all this is to change units of measure into seconds and meters. So everything is done here. So as we can see in the middle here, mass is equal to area, because it's in this column here for square meters. So like on the left here, you see meters to the second power is lined up with mass. And on the vertical axis, you can see that it's seconds to the 0 power, which is 1. And temperature, you see on the right of mass, is square meters per square second. And the Navier-Stokes equation of hydrodynamics. It's mysterious to some people, and it is in the column there of seconds to the minus 2 power. Now, these things are very standard in terms of, like, say, energy and force. Then and momentum are all shown at the bottom there, where the momentum is cubic meters per second, force is cubic meters per second squared, and energy is meters to the 4th power per second squared. All right, but then if we go to the electricity continuum, it becomes much more useful to an electrical engineer or to a physicist, where we see that now the Coulomb is given the area attribute, the aspect, and the Henry, interestingly, of an inductor, has no units. It's just a number of turns of a coil. No seconds, no meters. Now, permeability is per meter. Conductivity is seconds per meter. The ohm, like I was saying before, over here on the right, is just per second. And it's the same as the Tesla. Webers per square meter is per second. It's the number of lines of flux passing by per second. All right, so we're about ready to go on to some of the algebra in here. So that's down at the bottom of this page. All right, there it is. I started on May 8th of this year, writing down this essay. So here's how I calculate mass equals area using the composite formula that I showed you earlier. Old science claimed that some units of measure cannot be factored, like the kilogram or the coulomb. Those are just primitive things that do not have any smaller details within them. Like a prime number, they cannot be factored into things. But I've discovered that the kilogram is a composite number which has two factors, meters times meters. And here's the summary of how that is figured. I'll tell you the summary first, and then I'll give you all the details. Step 1, understand that mobility, mu, has effectively the same units of measure as conductance, inverse resistance. And then I'll use Ohm's law and a transistor current equation to find that charge is an area of something. So Q equals square meters. Now, 3, understand that the kilogram in standard science cannot be isolated to one side of the formula to be equal to any simple term on the other side. And I've tried it. What you get is kilogram equals kilogram. No matter how many energy equations you manipulate through algebraic rules, you can't really isolate the kilogram as being equal to something else, except with my new advancement I'm going to tell you about real soon. Okay, step 4. Use the energy equation, where energy equals force times distance, and the capacitance definition to bring mass and capacitance into one formula, because a capacitor can have energy. Now, step 5, bring farads and kilograms to one side of the formula, and the other side is left with only with meters and seconds. So that was the key breakthrough right there. Therefore, using logic, I will show that mass equals square meters and farads equals square seconds. This is now detailed for the next 14 minutes of our half-hour show today. All right, so step 1, Ohm's law, we see that G is the inverse resistance. So if the voltage equals IR, then the current equals GV. So there's Ohm's law. The second line here is the transistor equation here, the MOSFET current equation here, where it's I equals mu C0 VGS minus VT squared is a typical equation. So basically it's voltage squared times the capacitance area and this mobility mu. So you see the number C is in farads, V is in volts, and now one important step is I'm setting G equal to mu. I'm saying that they are the same thing because consider the definitions here. All right, I'm getting my books ready to show you here. Let's see, my notebook. I was saying that what is mobility? Well, the units of mobility is centimeters squared per volt second. And what that means, it's the velocity of an electron per electric field. Now, the electron mobility does not have the letter Q in it, but the conductivity, conductance, G, does have Q in the formula. So that's where the equality comes in. They're both about electrons passing by an area. In fact, they're equal in every way except magnitude. The mobility has the same physics as a resistance. It's just a matter of, is the number a million times bigger than the resistance or a million times smaller? There's no different physics going on here. So I'm going to go through this without your approval, and then you can review all this in slow motion later on. All right, so G is equal to the charge times the mobility times the number of charges times the area divided by the length. So that's the definition of G, the conductance. Notice that mu is in there, so it's equal to mu times a charge and a bunch of numbers, areas and things. Now, G is defined with Q in the definition here. Mu is defined without Q, but mu is the electron mobility. So in the words, the definition of mu is electron mobility, but they never mention the electron. G is conductance, but they specifically put Q in there. As a result, I'm able to modify this, and that by doing these algebraic manipulations here of what all these definitions are, we see the most important thing right here. Mobility equals square meters per volt second. Conductance equals coulombs per volt second. If they are measuring the same thing, that means that meter squared equals coulombs. All right, good. We've established that fact. The coulomb is a square meter. I don't need your approval for this. You can review the steps in slow motion tomorrow if you want. All right, so now charges area. We've established that. Charges area, because the properties of G and mu are the same for making current. They only differ in magnitude. Why do they have two different types of values, mobility and conductance, if they're exactly the same thing, but they only differ in magnitude? It's a matter of language. Electron mobility has the word electron in it, so that is the difference. All right, so Q equals a square meter. And see, in step 3, we're in old science, the kilogram cannot be set to anything different. Let's see, go to step 4. Now, the energy equation here is that force times distance is there, and that the voltage is equal to energy divided by the charge. So the voltage equals kilogram per square second after you've canceled out those. And you get, therefore, these equations here, where we're starting to isolate the kilogram and the capacitance. And finally, we see that here it is, the composite formula. By doing algebra, you can see mass times capacitance equals square meters times square seconds. Now, using logic, you can say either mass is equal to square meters or mass could be equal to square seconds. But in these choices that I show here, choice number 1 is the best. But look at the other choices. Choice number 2, what if mass is really meters times seconds, and capacitance is meters times seconds? Well, that doesn't make sense because they're both the same. Or choice 3, what if mass is square meters times second and capacitance is a second? It's not as good because then capacitance equals conductance and mass equals a diffusion coefficient. Therefore, I'd pick choice number 1. Mass equals square meters, capacitance equals square seconds. Now, square seconds might seem strange to you, but really, Kepler came up with this a long time ago when Kepler's famous equation, his law, that the period cubed, no, the distance cubed divided by the period squared is a constant. So the period squared is time squared. So he was talking about square seconds hundreds of years ago. So, therefore, mass equals area is now proven. I'm going to just get a drink here, so why don't we just look at the nice picture here while I drink. Thank you very much. Now, I'm about to sign off in 5 minutes. Yes, and but I'm going to show you these periodic tables once again. So, in this one, I've showed you the meters on the vertical axis and the seconds on the horizontal axis. But in the 8-dimensional physics that I've been telling you about, I'm now switching to the possibility of having not meters and seconds, but eters and econds. Ah, there it is. You see, on the left, the vertical axis is in eters to the -1, eters to 0. So this enables some flexibility of exceeding the speed of light as a ratio, and then invoking eters and econds to give you license to have some velocity which might be higher than the speed of light. But other than that, you can often just use meters equals eters and seconds equals econds. And then we see that all of the electrical variables are given clear-cut definitions. Here's the farad. See, square seconds. Right there, just like we all derived a minute ago. Mobility is seconds. The Henry is nothing. Like I was saying, the unit of measure for an inductor, how many Henrys is that induction coil? Well, it is 50 turns of copper. That's all it is, 50 something. There's no units. Meters to the 0 power, seconds to the 0 power. And I talked about ohms before, is per second. And there's a lot of other very interesting units of measure. There's the magnetic field, is a velocity. Yeah, we just talked about that. The H field here of Maxwell's equations, that's in meters per second. That's a velocity. And that's arrived at by using the mass equals area theory. Simply substitute, anywhere it says kilogram, substitute square meters. Anywhere it says coulomb, substitute square meters. And you get these formulas here. We see the Weber and the ampere are the same types of things. Down here, there it is. Weber and ampere is a flux, just like a bond or a wave function. Schrodinger's equation is a flux. Ether squared per econd. That's a wave function. And then we can now wind up the presentation for today, just showing that we've covered this part here already about the old and new wave. For example, the H field, instead of amperes per meter, the H field is a velocity. So that concludes the technical portion here. I'm about finished for today. I'm on every Monday, Wednesday, and Friday at 20 hours, Greenwich Mean Time. My name is Alan Folmsby, and these lectures are on theoretical physics. They are not approved by educators.